When we build geolocation-based features like find nearby restaurant or find nearby friends, what are the common approaches? Choosing the right approach is crucial for performance and scalability. In this video, let's first explore geohashing together. It is a popular geospatial indexing method that encodes geolocations into hashes to speed up searches. Then, I will provide a brief overview of geospatial capabilities in various enterprise databases. Explore the reasons why Redfin migrated their geospatial functions from MySql to Postgres. Finally, we'll dive into a hands-on demo, showcase how to use geospatial queries in MongoDB to efficiently manage and query location-based data. If you are a developer planning to develop geospatial features or applications, I hope this video helps. Let's start. Geohashing uses a base 32 encoding mechanism, where each character is ranging from digits 0 to 9, with addition 22 letters A to V. The first character of geohashing divides the entire Earth into 32 cells. Each subsequent character increases the position by recursively dividing the parent cell into 32 smaller subcells. Let's check out this online visualization tool for better understanding how it works. As you can see, when we append characters into the string, the map becomes more precise. The length of the hash string is called position. Let's check out this picture. It breaks down how position level corresponding to cell size. When position is 9, the length of each cell is around 4.8 meter times 4.8 meter, which is already pretty precise. There are many open source libraries available for different programming languages, such as geohashing for Python, make it easy to work with geohashing. When designing a system like finding nearby restaurants, application can encode the restaurant latitude and longitude coordinates into geohashes. Then the hash string can be stored along with the restaurant information. To find nearby restaurant for given location, you can query a database using a geohashing prefix. The SQL is pretty much like this. Databases can create indexes on geohashing string. This query can be executed very fast. There is an issue if you look into the details. For example, in this case, this geohash value is on the edge of the boundary. It is located on the top left corner. If you want to find neighboring restaurants, simply use the parent substring is not sufficient. It can cause a skewed search space. The actual neighborhoods of this cell belong to completely different hash prefixes. Implementation need to carefully find the neighborhood's geohashing values, then search in records based on those values. If you don't want to implement the nitty-gritty algorithms by yourself, plenty of enterprise databases have implemented geospatial features. Both MySql and Postgres provide similar features. Housing website Redfin wrote a blog describing their experience with MySql and Postgres. They migrated from MySql to Postgres for better GIS performance. Let's check out the blog together, which is pretty interesting. In MySql, a normal index cannot include spatial columns, and a spatial index cannot include normal columns. In other words, developers can't create an index mixed with spatial columns and other types of columns. For example, a search for all past sales in San Francisco Bay Area that had one bedroom but sold for over $10 million resulted in a killer query. However, using PostGIS, we could create an index on geospatial typed columns as well as other types. Besides the index, PostGIS offers sophisticated geographical functionalities, such as stcontains, stIntersects, stWithin, handles spatial relationships. There are various data types to store geolocation values in PostGIS as well, like point, lines, box, polygon, circle. MongoDB also provides geospatial features. I will use it to demonstrate. Because Mongo Atlas is completely free if the total storage is under 512 megabytes, it is perfect for demo purposes. Other databases are pretty similar. Set up Mongo instance is pretty simple with just a few clicks on their website. This is Mongo Compass. It is a local connector, allows user to connect to the cloud instance. I have already loaded the location data into the instance. As you can see, the location field is a type of points along with their latitude and longitude. In order to use geospatial queries, the location field has to be indexed. In MongoDB, this particular index is called 2D sphere. It allows geospatial queries on the Earth-like sphere. This command will create the 2D index on the geolocation field. I already did this. Let's first explore their polygon features. In this example, query is going to add a polygon geometry with 4 vertices. GeoWithin operator will return points within that polygon. Notice that the first coordinate and the last coordinate must be the same. As you can see, Central Park is inside the rectangle. Second, let's explore the near operator. It queries the collection. Any documents that have a location field within 5,000 meters will be returned. As you can see, airport and Central Park are returned. Third, geoIntersection operator queries for location data that intersects with a GeoJSON object. In this case, Central Park is returned. This is going to wrap up our session. I hope you have learned something. See you next time.